Good morning and welcome to this session with the oxidation of fatty acids. Uh, Today we are going to discuss fatty acid with oxidation of fatty acids with the following learning objectives. So you'll be able to describe activation of fatty acids and transport of activated fatty acids into the mitochondrial matrix. In this session, you will be able to outline the beta oxidation pathways. Then you will be able to describe the energetics of beta oxidation, and also you will be able to describe the regulation of beta oxidation. So let us go to the next slide. In this slide, let us have a brief overview of uh, oxidation and biosynthesis of fatty acids. This is oxidation. There's the first one, you see. We are going to see this part today, oxidation of fatty acid that is taking place in the mitochondria. So during fasting or during starvation or during in diabetes mellitus, when the insulin level is low, so there will be increased in glucagon, and this will lead to lipolysis of the triacylglycerols in the adipose tissues, leading to increased production of free fatty acids. This is free fatty acids. So this free fatty acids will then undergo beta oxidation to produce acetyl-CoAs, and this will ultimately lead to formation of ketone bodies. Or some of the acetyl-CoA may be oxidized in the TCA cycle to carbon dioxide and water. And in the on the other side, you can see during fat state, or when the insulin level is high, during fat state, what you see is there is increased glycolysis. This insulin will activate glycolysis, so there will be increased formation of pyruvate, and this pyruvate will be ultimately converted into acetyl-CoA, and this acetyl-CoA will undergo lipogenesis, that is synthesis of lipids or the fatty acids from the acetyl-CoA. So fatty acids will be produced in increased amount, and these fatty acids will ultimately undergo esterification with glycerol to form triacylglycerols, and it will be deposited in the adipose tissues. So this whole process is taking place under the influence of insulin, and this side you have seen the whole process is taking place under the influence of glucagon. Now, when you take your diet may contain different types of fatty acids. So these different types of fatty acids will be oxidized through different oxidative pathways. So the unbranched saturated event chain fatty acids with chain length between 18 to 20 carbons will be oxidized by beta oxidation pathway, and this is what we are going to see today in this class. And if the fatty acid contains odd number of carbon atoms, then they will be catabolized, or they will be oxidized to this little modified pathway that is called oxidation of odd chain fatty acid. Okay, then unsaturated fatty acids will be also oxidized with a modified beta oxidation pathway. There should be some, this unsaturated fatty acid needs some modifications so that it can be processed in the beta oxidation. Then methylated fatty acids will be undergoing alpha oxidation. Then very long chain fatty acids will be oxidized through peroxismal oxidation pathways, and the medium chain fatty acids will be oxidized to the omega oxidation. So these are the different oxidative pathways, but in this class we are going to discuss only about beta oxidation of fatty acids, which is oxidizing unbranched saturated even chain fatty acids with chain length from 18 to 20 carbons. Now let us have a brief overview of beta oxidation of fatty acid. Okay, so this is a 16 carbon palmitoyl or palmitic acid you have taken. So if this palmitic acid is undergoing beta oxidation, what is happening is in each cycle of beta oxidation, two carbon acetyl-CoA molecule will be released. You can see here acetyl-CoA molecule is released in every cycle of beta oxidation. So these palmityl-CoA being 16 carbon, this will undergo 7 cycles of beta oxidation and produces how many acetyl-CoA? 8 acetyl-CoAs will be produced. Because in each cycle, two carbon molecule acetyl-CoA will be released. So ultimately, when it undergoes 7 cycles of beta oxidation, you will get total of 8 acetyl-CoAs. And in the beta oxidation process, FADH2 and NADH2 also will be generated, and this FADH2 and NADH2 can enter the mitochondrial matrix through electron transport chain and produce this FADH can produce 1.5 ATP, and this NADH can produce 2.5 ATP when it is processed in the in the mitochondrial matrix with the help of ATP synthase. They will form ATP. Okay. Now, activation of fatty acid. This is the first step in beta oxidation. Before the fatty acid can enter into the mitochondrial matrix, it needs to be activated to its activated form, that is acyl-CoA form. So this activation step is catalyzed by the enzyme acyl-CoA synthetase, and this activation process is taking place in the cytosol, and rest of the steps of beta oxidation will be taking place in the mitochondria. So this first step, that is activation of the fatty acid, takes place in the cytosol, and it requires coenzyme A, ATP, and magnesium. So the enzyme is acyl-CoA synthetase, and this reaction utilizes two phosphate bonds. So ATP is ultimately hydrolyzed into AMP and this inorganic pyrophosphate, and this inorganic pyrophosphate will be ultimately broken down into two molecules of inorganic phosphate, and this will drive the reaction forward. So you get acyl-CoA. This is the activated fatty acid. Now, this activated fatty acid, that is this is acyl-CoA that has been formed by this reaction that we have seen in the previous slide. So this acyl-CoA can now enter the mitochondrial matrix through the outer mitochondrial membrane. It can pass through, and it reaches the intermembranous space. In the intermembranous space, it combines with carnitine or reacts with carnitine and forms acyl-carnitine, and the CoA is released, and this reaction is catalyzed by CPT1, that is carnitine palmitoyl transferase 1. And this acyl-carnitine can now be translocated into the inner mitochondrial matrix with the help of enzyme carnitine acyl-carnitine translocase, or simply you can say translocase. So it will now reach the inner mitochondrial matrix, and in the mitochondrial matrix it will be again split into carnitine and acyl-CoA. So CoA is needed here, and the enzyme catalyzing this reaction is carnitine palmitoyl transferase 2. So now you get carnitine and acyl-CoA. The acyl-CoA will undergo beta oxidation, and the carnitine can it will be translocated again into the intermembranous space, and again it can take part in bringing more acyl-CoA into the mitochondrial matrix. So now the acyl-CoA is inside the mitochondrial matrix, and this will undergo beta oxidation. Let us see all the steps of beta oxidation in the next slide. So the steps of beta oxidation, It is a four enzyme catalyzed reactions, series of four enzyme catalyzed reactions, which ultimately uh, leads to release of acetyl-CoA, two carbon molecule acetyl-CoA in every cycle of beta oxidation. So first enzyme is acyl-CoA dehydrogenase, second is enoyl-CoA hydratase, third is again dehydrogenase enzyme, and third one is thiolase. Since this picture is very small, I'd like to show you each reaction steps in separate slides in the following slides. Let's go. So this is the first one, enlarged view of the first reactions of beta oxidation proper. So this step is catalyzed by acyl-CoA dehydrogenase enzyme. So it is a dehydrogenase enzyme. So what is the coenzyme here? Coenzyme is FAD. FAD is reduced to FADH2, and this acyl-CoA is oxidized to delta 2 transenol CoA. That means from the second and third carbon, hydrogen ions are removed and they are taken up by the FAD to form FADH2. So in this compound, there is introduction of double bonds between 2 and 3 because it has lost two hydrogen ions, one from each carbon. So there is double bond. So this is delta 2 transenol CoA. That means double bond in the second and third carbon, and they are in the trans form. So delta 2 transenol CoA. And this FADH2, it will be transported to the electrotransport chain, and it can lead to generation of 1.5 ATP. This is actually ATP. Next reaction is the delta 2 transenol CoA now undergoes another reaction that is catalyzed by delta 2 enoyl CoA hydratase. That means there is addition of water molecule into this molecule. So it forms 3-hydroxyacyl CoA. So in the third carbon, you can see in the third carbon there is addition of hydroxyl group. There is addition of hydroxyl group to this third carbon, and another hydrogen is added to this second carbon. So the double bond between 2 to 3 is removed, and now you get a compound that is called Al3-hydroxyacyl CoA. And why we write Al is that this delta 2 enoyl CoA hydratase can produce only this L isomer. It can produce only L isomer, so we mentioned here that it is L isomer of 3-hydroxyacyl CoA. Next reaction is again it is a dehydrogenase reaction, and the enzyme is L3-hydroxyacyl CoA dehydrogenase. So again this 3-hydroxyacyl CoA is undergoing oxidation reaction. It is oxidized to 3-ketoacyl CoA and NAD. Coenzyme used here is NAD. NAD is reduced to NADH, and this NADH through electron transport chain it can produce 2.5 ATP. 2.5 ATP per NADH molecule in the mitochondria. It can produce 2.5 ATP. Now, what is the reaction here? Here it is again dehydrogenase reaction. So the hydrogen from this third carbon hydroxyl group is lost, and another yes, and this one. These two are lost, so there is introduction of a double bond in the third carbon. So it is a keto group now. So 3 keto, and this is the acyl CoA. So 3 keto acyl CoA. 3 keto acyl CoA. So this is the compound form. In the next, these 3 keto acyl CoA undergo cleavage reaction by enzyme thiolase, and this acquires coenzyme A as a coenzyme. So in this reaction, there is removal cleavage of this two carbon compound. You can see the line drawn here. So this molecule will be cleaved here, and this two carbon compound acetyl CoA will be released. This is acetyl CoA released, and you will get another molecule of acyl CoA, which will be two carbon less than the original acyl CoA that was undergoing with oxidation. And this acyl CoA again, it will undergo the second round, another round of with oxidation. Then it will undergo this steps 2 to 5. This process will be repeated till this acyl CoA is completely oxidized into acetyl CoA. So when the 16 carbon palmitic acid is undergoing beta oxidation, it will undergo 7 cycles of beta oxidation, 7 cycles of beta oxidation, beta oxidation, 7 cycles of beta oxidation it will undergo and produce how many acetyl CoA? 8 acetyl CoA will be produced, because in the last cycle both the compounds will be acetyl CoA, so you will get acetyl CoA 8. And in each cycle of beta oxidation you are getting 1 FADH2, and in each cycle you are getting 1 NADH plus H. So in 7 cycles we will be getting 7 NADH2 and FADH2 and 7 NADH. So in each cycle this NADH can produce 1.5 ATP. So in 7 cycles it will produce into 7, that will be 10.5, and here it will produce 2.5 per NADH into 7 NADH, that will lead to production of 17.5. And acetyl CoA, one molecule of acetyl CoA, when it is processed through TCH cycle, it can produce 10 ATPs. So 10 into 8, it will be 80. So 8 ATPs, 8 acetyl CoA, 1 acetyl CoA 10, so total they can produce 80. So if you add all these, it is coming to 108 ATP. But you have to remember that during activation process we have utilized phosphate bonds equivalent to 2 ATP. Therefore 2 has to be subtracted. So net production of ATP from this 16 carbon palmitoyl CoA, you are getting 106 ATP. So this is the energetics. So you can calculate any number of energetics for any number of carbon atoms. But simply what you have to do is, suppose if there are 18 carbon, then it will undergo 8 cycles, isn't it? 8 cycles. 8 into 2 is 16. Then last 2. So it will undergo 8 cycles, and it will produce 9 acetyl CoA. 9 acetyl CoA will be produced, and how many NADH? How many FADH? It will produce 8 FADH, 2 and 8 NADH plus H. So that way you can calculate the number of ATPs that will be produced. So this 9 into 10 will produce 90, and this 8 into 1.5, how much? 1.5, and 8 into 2.5, how much? So you can calculate your number of ATPs, but at the end you have to subtract 2 from the whatever number you get. You have to subtract 2. That will be the net ATP produced from that particular fatty acid after beta oxidation. Regulation of beta oxidation of fatty acids. The regulation of beta oxidation of fatty acid may be brought about by regulating the supply of fatty acids, that is free fatty acids. So by increasing or decreasing the quantity of free fatty acids in the blood, the beta oxidation may be reduced or increased. And secondly, by controlling the activity of the enzyme carnitine palmitoyltransferase 1, which is the enzyme that leads the acyl-CoA inside the mitochondrial matrix. So by controlling the activity of this enzyme, the beta oxidation may be controlled. But basically, the beta oxidation of this fatty acids is ultimately controlled by the insulin-glucagon ratio. When insulin-glucagon ratio is high, which you see in the case of fat state, there will be lipogenesis, that is synthesis of lipids. And when the insulin-glucagon ratio is low, which you see in case of fasting state, the lipolysis will take place. So during lipolysis, when the insulin-glucagon ratio is low, that means there is increased amount of glucagon in the blood, and this will cause lipolysis, and lipolysis will lead to production of increased amount of free fatty acids in the blood, and these free fatty acids will be activated to acyl-CoA, and then this acyl-CoA can enter the mitochondrial matrix through carnitine settle, and then it can undergo beta oxidation to produce acetyl-CoA, and this acetyl-CoA will be ultimately lead to production of ketone bodies, and therefore during fasting or in prolonged starvation or in diabetes mellitus, there may be excessive production of ketone bodies, which can lead to ketoacidosis. Or some of the acetyl-CoA may be oxidized in the TCA cycle to carbon dioxide and water. Now, when the insulin level is high, that is during fat state, what is happening is there will be excess glucose in the blood. So this glucose, under the influence of insulin, it will be undergoing glycolysis to produce acetyl-CoA, and under the influence of insulin, this acetyl-CoA will undergo lipogenesis to produce the fatty acids or the palmitate. So this insulin will influence the enzyme acetyl-CoA carboxylase, which is the rate limiting enzyme of this lipogenesis pathway. So this insulin will activate this enzyme, so lipogenesis will take place during fat state. And during fat state, in the process of lipogenesis, this malonyl-CoA intermediates of this lipogenesis can inhibit enzyme carnitine palmitoyltransferase 1. That means during the process of lipogenesis, when the lipogenesis is proceeding, when the fatty acids are being formed, this lipolysis pathway will be blocked. So not lipolysis actually, but the transport of this activated fatty acids into the mitochondria will be impaired. So the fatty acids cannot enter the mitochondrial matrix, and therefore beta oxidation will be hampered. There will be no beta oxidation of fatty acids because it is not entering the mitochondria during during fat state. Okay, and because this malonyl-CoA is inhibiting this enzyme carnitine palmitoyltransferase 1, and during the fat state, there will be some amount of free fatty acids in the blood which is coming from your diet. So these free fatty acids, after being converted to acyl-CoA, this acyl-CoA it cannot proceed, it cannot enter the inner mitochondrial matrix because malonyl is inhibiting this enzyme. Therefore, these acyl-CoA may be esterified with glycerols to form acyl glycerols, and then this acyl glycerols may be incorporated into VLDL, and it will be transported in the blood to the different tissues in the body. So that is how ultimately the insulin-glucagon ratio is controlling these two processes, lipogenesis and lipolysis. So altered, once again I'm telling you, altered insulin glucagon ratio, that is when the insulin is low and glucagon is high. In case of fasting state, free fatty acids will be produced in excessive amounts, and they will go enter the enter this mitochondrial matrix and undergo beta oxidation, and therefore it will lead to formation of increased amount of ketone bodies. So during fasting or starvation, or in diabetes mellitus, there may be ketoacidosis. Ketoacidosis. It can lead to ketoacidosis. Okay, so that's all. Defects in beta oxidation can be brought about by the enzyme deficiencies of beta oxidation. One of the most common enzyme that is deficient in beta oxidation is the medium chain acyl-CoA dehydrogenase. So this is the first enzyme, acyl-CoA dehydrogenase. So medium chain acyl-CoA dehydrogenase is most commonly deficient. So when this enzyme is deficient, the oxidation of medium chain fatty acid is impaired, and this leads to symptoms like vomiting, lethargy, non-ketotic hypoglycemia, and even coma. So I would like to explain here what is non-ketotic hypoglycemia. Since this enzyme is deficient, the beta oxidation will not proceed, and therefore acetyl-CoAs are not formed, and therefore there is no ketone bodies formed. Therefore, non-ketotic, we call non-ketotic, and hypoglycemia. Patient will have hypoglycemia, so non-ketotic hypoglycemia. Since the medium chain fatty acids are not able to be oxidized to this beta oxidation pathway due to the enzyme deficiency, they will be oxidized through another alternative pathway that is called omega oxidation. Okay, so actually the medium chain fatty acids are oxidized through omega chain fatty acid as an alternative part, and now all the medium chain fatty acids will be oxidized to this omega oxidation, and this will lead to production of increased amounts of dicarboxylic acids, and these dicarboxylic acids will be excreted in the urine, and that is called dicarboxylic aciduria. This is a clinical condition. So that's all. Next, there may be deficiency of carnitine, which is usually seen in preterm newborn infants due to inadequate biosynthesis or due to renal leakage. So there is deficiency of carnitine, and this is characterized by non-ketotic hypoglycemia when liver is affected, and muscle cramps and muscle weakness when muscle are involved or muscle is involved. So treatment will be oral supplementation with carnitine. Carnitine, this translocase enzyme can also be defective. When this is defective, and then there will be muscle cramps precipitated by fasting. So when you do fasting, there will be muscle cramps, because during fasting, lipolysis will take place, but these lipids cannot enter the mitochondria to produce ATP. So there will be muscle cramps precipitated by fasting, exercise, or when you take high fat diet, because they are not going to be they are not going inside the mitochondria to be able to process in the beta oxidation. So there will be muscle cramps. Inherited CPT1 deficiency can also be there, and CPT2 deficiency can also be there. In case of CPT1 deficiency, it affects only the liver, resulting in reduced beta oxidation of fatty acid. Reduced fatty acid oxidation will be there, and therefore there will be reduced ketogenesis, and patient will suffer from hypoglycemia. Similarly, in CPT2 deficiency, it will primarily affect the skeletal muscles, and only in severe cases liver will be affected, and the symptoms will be same. Next is Jamaican vomiting sickness. What is this Jamaican vomiting sickness? This disease occurs when one consumes unripe fruit of ackee tree, this beautiful fruit of ackee tree. This fruit contains a compound that is called hypoglycine, and this hypoglycine can inactivate the enzymes medium chain and short chain acyl-CoA dehydrogenase, which is the enzymes of beta oxidation. Therefore, beta oxidation will be inhibited and patient will suffer from hypoglycemia, and this may be fatal. So this is all about beta oxidation and its diseases due to defects in enzymes of beta oxidation and the related things that we have discussed. So that's all for this class. Okay, thank you.